702 and Cape Talk.
The Naked Scientist.
That means we answer all your questions from the world of science. Good morning to you, Chris.
Morning, Eusebius.
We start this week by having a look at the science story that is quite interesting about how to store energy from renewables.
Yes, indeed. The world is very worried about climate change, and at the moment, one of the biggest emitters of climate change gases like carbon dioxide is energy production, chiefly for electricity, but also household heat. Now, the issue is that many countries are beginning to increase their use of renewables, things like wind power and solar power. And in countries like the UK, they're set to exceed more than a third of the generating capacity of those countries in the near future. Now, what we can't do is to tell the wind to blow or the sun to shine on demand. We can turn a power station on when we need energy, but we can't do that with the weather. So what we do have is this boom and bust situation where we have good times where it's very sunny or very windy, big surf feet of power, but then we have times when we really need power and there's just not enough generating capacity. What we need is some kind of energy sponge that can sit between the two and soak up the extra energy during the good times so we can release it back to the grid in the bad times. And there's an interesting analysis in the journal Nature Energy this week by researchers at the University of Edinburgh. This is Stuart Hazeldine and his colleagues. And they've done a feasibility study where they've looked at the prospect of using surplus energy from a power grid, using this to run compressors, which take air and squeeze it deep underground into porous sandstone rocks down, in some cases, new boreholes, but in many cases under existing boreholes that have been used for other sorts of practices, like the recovery of oil and gas in the past. Now, that stored gas under pressure can stay there for a very long period of time, and then when you need the energy back, you can open the taps and let the gas out, and the escaping gas can be used to drive turbines in various ways, and that driving of turbines can then be used to recover electricity. They've done some cost-benefit analysis. They think it'll be about 50 to 55% efficient. In other words, you get back about half the energy you put in doing this process. That means it will cost about 3 or 4 times as much per unit of electricity than we currently get when we burn some gas, for example. But it's a non-polluting way of doing this. And in certain countries like the UK, where you've got lots of offshore sandstone that you could do this in, you don't have to do it where there are people. So the geological risk of creating, for instance, some kind of earthquake or something, or mild ground tremor, those risks are mitigated. But Stuart Hazeldine is at odds to emphasise that this could be applied anywhere in the world, and it may actually be one wherever the right rock formations exist, and therefore it might be a very useful way to currently turn what we have as a wasted commodity, a lot of sunlight, a lot of wind, for example, into useful stores of energy that can then be used when we actually need energy without having to pollute the planet.
Fascinating. Let's go to Santon. Colette's on Santon. Are you experiencing the question that I know you have for Chris?
Yes, because I've always wanted to speak to the naked scientist.
Don't worry, he's going to know our in-joke in a second. What's your question?
Why do we get butterflies, not the ones in nature, but when you're nervous or when you see your crush, whatever causes it?
Or when you're about to speak to the naked scientist?
Yes.
Happens to me when I'm about to speak to my bank manager. Hi, Colette. This is a very good question. Who have you got a crush on then?
Wait, live on radio? No, not doing that.
No, the reason we do this, it's all part of what's called your fight or flight reaction. You have part of your nervous system over which you have no control. It's called the autonomic nervous system, and it's there to take care of the things that you've got better things to do than worry about. It does things like make sure that you don't wet yourself. It does things like control your blood pressure. It keeps you breathing. It focuses your eyes for you. So it's taking care of all these jobs, and it's also anticipating danger. And when we anticipate danger or threat or excitement, then this autonomic system kicks in, and specifically one part of it called the sympathetic nervous system. Now, the sympathetic nervous system is associated with the release of large amounts of the chemical adrenaline and its relative noradrenaline into your bloodstream. And this has a number of effects, but one of them is it makes your heart beat faster and more forcefully. So you're very conscious often of having a thudding heart, and that's why you get that sensation of a beating heart and a palpitation when you're nervous about something. It also has the effect of shutting off your intestines. What I mean by that is that when you are preparing to run away, what you don't want to be doing is diverting huge amounts of blood and energy into your intestines to digest your dinner, because if you're robbing your muscles of blood to digest your dinner, those muscles are not going to work as well. So one of the actions of the sympathetic nervous system is to strongly switch off the musculature of the gut and divert the resources to other bits of the body, like for instance, your muscles. So part of the butterflies and the sinking sensation in the stomach that we describe is the sympathetic nervous system deactivating your guts and all the muscles relaxing and your stomach relaxing and everything stopping. And that is part of what we describe as butterflies in our stomach. It's your body preparing you for action and turning off your intestines so that you can either run away or kiss someone, I suppose.
LaQuisha, good morning.
Good morning. Hi, how are you, Studios and the Naked Scientist?
Very well, thank you.
I'm wanting to know why when someone hums a tune in their head, you can get the tune so correctly, but when you want to sing it, it becomes false, and you know immediately that you're wrong. It's not right.
Morning, LaQuisha. What song have you got going around in your head?
No, it's sometimes I'll be singing any song or humming it in my head or thinking it in my head, and then I want to sing it out, and immediately it comes up false, and I've got to try and get back to the right key.
Yeah, can you do us a demonstration of what song will come out wrong?
Definitely not.
Well, I think part of it is that the way you normally listen to music is by listening to it through your ears, not hearing it inside your head. So part of it could be that when it comes out of your mouth, you realise that actually what you're listening to in your head, because it hasn't gone through the filter of your ears, might be a bit off anyway, because you're fooling yourself into thinking it sounds right in your head. But more importantly, what's probably going on is the part of the brain that decodes and presents sounds into your consciousness is not necessarily well connected to the expressive parts of the brain that are needed to make those sounds. Because if you think about it, in order to sing or talk or do anything, in fact, you've got to engage the motor system in your brain, the region that plans out and executes movements. To sing, make movements, talk, they are all complex motor patterns of activity. Now, to translate the sounds you've heard into those patterns, unless you've practiced how to do that, you're not immediately going to be able to do it. So although you think you know what it should sound like, when you actually try to do it, unless you have a few goes at it, it's going to be really tricky. It's a bit like if you watch someone, I don't know, jumping and doing somersaults on a trampoline, you could think, yeah, I just bounce up and down a few times and then I'll just flip over and that'll happen. It won't happen until you've had a go at practicing it, because you've got to learn how to put into practice and execute the right pattern of movements to get what's in your mind's eye, what you're planning to do, and turn that actually into reality. And so we have to make mistakes in order to get it right. And the brain has a system to refine things. So the brain compares what it wants to do with what actually happens, and then it generates an error correction signal by comparing what should have happened and what actually happened, and then it uses the error correction signal to make the next time you do it a bit better. And there's a region of the brain called the cerebellum, which is Latin for mini brain, which sits right at the back underneath your brain, and this is responsible for a lot of these executed very fine movements and getting them to be absolutely perfect with practice. So that's why when you start singing, it doesn't come out quite right the first time.
Paul, good morning.
What I'd like to know is I've been reading a lot about vitamin K2, the MK7 variety, which apparently redirects calcium away from the arteries to the bones. I'd like to know whether this, in fact, is actually effective or not.
Yeah, hi Paul.
Chris?
So Paul is asking about vitamin K, and vitamin K is an essential component of our diet. We need it because it's important in blood clotting. And if you don't have enough vitamin K, then your blood doesn't clot properly, and it's an important system in the blood coagulation cascade. It makes an important contribution to that. I've not heard of anyone suggesting that vitamin K could be used as a way to unclog arteries. I'd need to see the evidence on that, Paul. So if you've got some kind of published reference or some kind of product that you can send me the details of, I'll certainly have a look if I have a chance, and we'll see if we can get to the bottom of it. But I'm not come across people using vitamin K as an anti-atheroma agent before. If you want to just drop me a line on Twitter, it's @NakedScientist, or you can email chris@thenakedscientist.com, and I'll see what I can do.
Jabeen, good morning.
Hi, good morning, Chris and Eusebius. I just wanted to find out about the use of aluminium foil in baking and cooking and drying. Is it safe to cook your food in direct contact with aluminium foil?
Yeah, this is a subject which has been looked at a number of times over the years and has a bit of a checkered history. The reason people are concerned about aluminium is that when people looked at the brains of people with some forms of dementia, in other words, atrophy of their nervous system with age, and specifically diseases like Alzheimer's disease, they saw that there's a build-up in those brains of these bits of protein, which are called beta amyloid, and they form lumps or plaques in the brain, and those lumps or plaques seem to poison adjacent nerve cells, and so scientists believe that the accumulation of these proteins is what causes the neurodegeneration, the loss of nerve cells that characterises Alzheimer's disease. When they looked more closely inside some of those plaques, you often find in there accumulations of metals, including things like aluminium. And so some people have suggested that perhaps what starts this process off in the first place is a build-up or a deposition of aluminium in the brain, and so aluminium triggers the initial deposition of these plaques. The thing is, though, that these plaques are abnormal. The anatomy where they are is abnormal, and they're also very sticky because the proteins that build up there are sticky proteins. So if you have small, highly charged metal atoms like aluminium, it may well be that actually the plaque is there and then the aluminium goes and builds up in it rather than the aluminium coming first. So we're not sure whether the aluminium causes the plaques or the plaques cause an increased likelihood of finding aluminium there. So in order to be safe, what people suggest is that because if you cook very acidic foodstuffs in an aluminium pot, you will liberate more aluminium from the pot, you should avoid doing that. So don't cook things like rhubarb and other fruits that will be very acidic in your aluminium pots. Use your iron pots for that. But for general day-to-day baking, foil and that kind of thing, the amount of aluminium being liberated and getting into the food is vanishingly small, and it probably is not going to do you any harm whatsoever.
702 and Cape Talk.
The Naked Scientist.
21 minutes after 10 o'clock. John, good morning.
Good morning. Thanks for taking my call, Eusebius. A question on the physics side. When an aircraft takes off at sea level, how does the pilot know, or how do they measure the altitude above sea level? Because Johannesburg is about 1,700 meters above sea level. Does the aircraft fly a little higher getting to Johannesburg? How is it measured and how is it taken note of? I listen on the radio for the answer.
Thank you.
There's a range of ways of doing this. The altimeters are calibrated, so some aircraft know basically how high they've gone based on where they started from, and you recalibrate based on where you are. There are other ways of doing it digitally with clever satellite technology these days, so there's a range of ways of doing this. But yes, pilots do need to know where they're flying to, because obviously if they take off and they're at one altitude and they're landing somewhere quite different, then they need to know roughly what the ground altitude is that they're landing at relative to sea level, because otherwise their altimeter would be wrong. So yes, it's a good point you've raised. There's a range of ways of doing it. One of them is that, or the most fundamental one, is you've got to calibrate your equipment for where you're flying from and where you're flying to.
David, welcome to the show.
Good morning, thank you. I have a question regarding the paper in Nature Energy. Did they specify what gas would be used to compress underground? Because it could trigger acid mine drainage in certain areas, depending on the rocks in which they compress the air. And I'll listen on the radio. Thank you very much.
Thank you for that question. The answer is yes. If you look up the paper in Nature Energy this week, you'll see that what they're proposing to use is normal air. So that would be 80% nitrogen, about 20% oxygen, and some trace gases. There are some considerations here, because obviously when you compress gas, it gets hot. When you cool it, when you decompress it, it gets cold, and you'd have to take that into account because there's a risk of condensation of water, and the water that goes in could corrode the metal parts and damage your borehole. The other consideration is that the oxygen going in could react with things which are already in there and trigger either chemical changes. It could also be consumed by certain chemistries that are already in the rocks, or it could just seep away because it could react with things that are there, and that could reduce the gas volume a bit. They've considered these things in the paper and in their feasibility study, and they're pretty comfortable that what they're proposing is viable, and it shouldn't trigger any kind of onward effect like acid mine drainage, because these are sandstones, they're very deep underground, they're extensively spreading porous rocks, but they are geological formations that have been stable for millions of years, so there shouldn't be any risk of them releasing anything other than the trapped gas.
Greg, welcome to the show.
Good morning, Eusebius. Morning, Chris. I was wondering, with the melting of the world's ice, and more specifically Greenland, and that fresh water and salt water have different densities and don't readily mix, I was wondering, this water entering the Atlantic with a relatively small gap, could this affect the Gulf Stream? Could it jam or slow down the Gulf Stream?
Hello, Greg. The answer is Yes, and people have been doing a lot of studies on this. They're looking at how this conveyor of warm water, which arises in the Gulf of Mexico, down where Florida is, goes up the eastern seaboard of the US, crosses the Atlantic and arrives in Western Europe, and then passes up the west coast of the UK. And the energy delivery to that latitude is something along the lines of having several hundred gigawatt power stations pumping out heat all the time, all year round, which is why, despite the fact that London is about as far north as Moscow, the temperature right now in Moscow is about -20, the temperature in London is about 2. And it's because of all that energy arriving from the warm water, which keeps countries like the UK much warmer in winter than they should be. But mitigating this is that, as you say, you've got a lot of ice on places like Greenland and also the Arctic Circle and the Arctic ice sheet. As that water melts out, it is fresh water and it goes into the sea, and the fresh water has a different density to the salt water, and so the two interact and it's displacing the salt water downwards, and as a result it is causing a diminution, a reduction in the Gulf Stream. So one prediction of global warming, paradoxically, is that countries like the UK, which are currently benefiting from this warm stream of water, would actually get colder owing to global warming. It might make winters, some predictions suggest 1 or 2 degrees colder.
Jacob, good morning.
Hi, Eusebius. I just want to know, why is it that the abandoned house cracks faster than the occupied one?
I didn't catch the question. Sorry, say again.
I don't know. He wants to know why it is that abandoned houses, presumably their walls, I'm not sure, crack faster than ones that have people occupying them.
I think it's because the people who live in houses tend to take better care of them, look after them and repair the cracks, whereas when buildings are abandoned, they're probably abandoned for a couple of reasons. One, because they're about to fall down, hence the cracks, and B, because there's no one living in them to look after them, they tend to deteriorate faster, and as they deteriorate, cracking's part of that.
Thank you, Jacob. Papi, good morning.
Good morning. I'd love to know, what is the difference between warm water and cold water? Whenever you consume or you drink warm water, you don't go to the loo more often to urinate. But when you drink cold water, you go to the loo more often to urinate. What could be the reason?
I've never observed that. Is that true?
Well, there's a physiological reason why this might happen. So it's an interesting observation that you've made. There is something called cold diuresis. When we get very cold in wintertime, we do tend to go to the loo more often. And this is because your body's response to the cold is to shift blood away from your peripheries, so things like your fingers and toes and arms and legs, and push the blood centrally to keep your core warm, where your essential organs are, and so your nervous system can maintain a supply of warm blood. The effect of pushing blood centrally like that to save you from losing heat is to increase your central blood pressure. So your kidneys interpret that increased blood pressure as, I've got too much blood on board. So what the kidney does is to secrete more urine. So in other words, it filters more liquid off the blood and throws more urine away in order to normalise the blood pressure. Now, I don't know for sure if it's true. You'd probably have to drink an enormous number of cold drinks to make this happen. But when you drink a cold drink, of course, you are lowering your core blood pressure transiently. You're lowering your core temperature transiently a bit. This might lead to a slight increase in blood pressure centrally. It might therefore trigger the kidney to interpret this as, my blood pressure's too high, I need to throw some water away, and it therefore might transiently increase the production of urine. Worth bearing in mind, though, that when you drink anything, in order to produce a reasonable amount of urine, you need to drink in the first place, because what the kidney's doing is keeping your blood pressure and blood volume stable, and it does that by either saving water, if you are not drinking enough, or throwing away the excess. And when you drink anything, your body's going to get rid of the excess, chiefly as urine. So I suspect that there is a kernel of truth to this, but I suspect the effect is going to be quite subtle and quite small compared with if you were to go and go out on a very cold day and get very cold.
Thank you, Chris. We'll do it again next week. Thanks so much for sharing that with us.
I'm looking forward to it. Thank you very much. Bye, everybody.